Let's review what a poset is. We have seen before that a poset is a set in which there is a relation of order, which means that satisfy the properties reflexive, antisymmetric, and transitive. In the graph of this poset here, let's review how we read actually a poset. So remember that the properties transitive are implicit in the diagram. The property reflexive is also intrinsic. I mean, we don't write arrows like this, but we know that in a poset each element is related to itself. And we also don't write the direction of the relation. We know that G relates to D. So the direction in which we read the diagram is also implicit. So we can read in this diagram just as it is, for instance, that F is related to A, because we read the relation like this and this, the transitive, and we have the direction also is always up. For instance, let me remind you some examples of posets that we have seen before. So, for instance, in this case, the set P is the set of these numbers from 1 to 6, and the relation. Observe that the symbol of relation that we are using is not the symbol of less or equal, right? So, less or equal is like this. This symbol that we are using is like this, and with a line like this. So this symbol means the relation of order. So the relation of order can be whatever relation we have defined in each case. In this case, in this particular example, for instance, will be the relation divides. Even though this is not necessarily less than equal, in general, I'm going to call it just less or equal if there is not confusion. So in this case, when we have a particular one that the relation is divides, I will just say divide. But if we don't know what relation is, I may call this in general less or equal, even if we know that it's not necessarily less or equal. So in this diagram, for instance, we have that 1 divides 5. That's what is the meaning of this line here, right? So remember that this is an arrow like that. Also, we know that 2 divides itself, because we know that that arrow that is not there, we should understand it like that too. So 2 divides 2. And also 2 divides 6 and 2 divides 4. Another example, in this case, the set P is more complicated. The set P, the elements of the set P are sets also. So the elements are the empty set, the set only of the letter A, the set only of the letter B, the set of AC, the set of ABC. All these things are the elements of P. So that's why all these are the nodes of this poset. And the relation, less or equal, let's say, in this case, is this relation, is a subset of. So, how do we read this diagram? Well, we read, for instance, B is a subset of BC. We can read also B is a subset of AB. We can read also B is a subset of ABC, because remember the transitive here. You can also observe that empty set is a subset of everything, etc. This other example is a very particular poset when the relation less or equal, let's say, is the really less or equal relation between numbers. So then, if the numbers are just the numbers 0, 1, 2, we are saying here 0 is really less or equal than 1, 1 is less or equal than 2, 0 is less or equal than 2, 1 is less or equal than itself. So this is the example when the relation is exactly the relation less or equal. And here we have a relation, we don't know what relation is. We know that P in this case is the set of all the numbers from 1 to 12, it looks like. And we have here this relation, we don't know what relation is. Let's call it less or equal, this less or equal, right? So this order relation. And so with this less or equal relation, reading this Hasse diagram, we can say that 8 is less or equal than 5 in this relation. Okay? And we can say that 12 is less or equal than 10. We could also say that 11 is less or equal than 3 because we follow this, right? And so on. You can read here all the relations between the elements in this poset. So now that we remember what a poset is, so let me define now what means to be a lower bound of two elements. So in the first definition here, we are said that for a element to be a lower bound of two other elements, what have to happen? Well, essentially have to happen that have to be less or equal than both of them, where less or equal means this relation, right? Whatever relation is in our particular poset. So, for instance, what would be a lower bound for, say, C and D? What are lower bounds here? So you can stop here and think for a moment what would be lower bounds for these two elements, C and D. So the idea is we have to find which ones are less or equal than both. So for instance, do you think that A will be a lower bound? Well, no, because A is not less than C. That's it. So we see here that to be less has to be lower, right? So A is not less than C, for instance, so that's it. So A is not a lower bound. Let's check another one. What about B? Is B a lower bound? Well, B is no less than C. Again, B cannot be a lower bound. Let's check with C. Is C a lower bound for C and D? Have to be careful here. Well, C is less or equal than C, right? Remember the loops here. So that's fine. I mean, the first part, let's say, is satisfied. C is less or equal than C. But is C less or equal than D? It's not. So because of that, I mean, because that doesn't satisfy the second property, so it's not going to be a lower bound. So to be a lower bound for C and D have to be less than both. So the answer is C is not a lower bound for C and D. Let's keep going. For the same reasons, we can deduce that D is not going to be a lower bound for those. Let's see E. Is E a lower bound for C and D? Well, it's less than C, is fine, but it's not less than D. So C is not a lower bound either. And then F. Well, is it less than C? No. It's less than D, right? But it's not less than C, so it's not going to be a lower bound. What about G? Is G a lower bound for C and D? Well, G is less than C, and it's less than D. Good. So that's the first one that we got. So in the set of lower bounds, we got one of them, lower bounds for C and D. We got one of them. G is the first one. So G is a lower bound. So let's keep checking. Well, there is only one more to check. Let's check with H. Is H a lower bound? Well, the question is H less or equal than C? Well, it is, right? So this will be the path. So remember the transitive here. So H is less or equal than C. Is it less or equal than D? Well, it is also less or equal than D. So H is a lower bound too. So we have that these two numbers are lower bounds, so for C and D. What about the upper bounds? So we can see already that all these things here are too low, none of them are going to be upper bounds. But let's look careful at the other ones. So for instance, B. Well, B is not going to be either, right? So B, C is not less than B. That's what we need to check, right? I mean, in order to be an upper bound, we have to check that the C and D, that will be these ones, have to be less than the upper bound. So in this case, we can see that B doesn't satisfy that, right? Because C is no less than B. So C is not going to work either because D is no less than C. D is not going to work because of the same reason. Let's just try A, the only one that remains. So, is C less than A? Yeah, it is. Is D less than A? Yes, it is. So then we have that the upper bound for C and D, the only one that we got is A. A is an upper bound for those. Now, we see that in particular, the upper bounds and the lower bounds are not unique. Well, in this case, the upper bound is only one, right? But it could be more. And in case of the lower bounds, we see clearly that are more than one. So we are going to see that between all the lower bounds, we can choose which one is the biggest of the lowest bound. And between the upper bounds, we can choose which one is the smallest of them. So we are going to call it greatest lower bound is a lower bound, but with this other condition, that is, we find another lower bound, so these have to be bigger than it, meaning that it's the biggest of all possible lowest bounds. So, for instance, between C and D, we have calculated before that there were two lowest bounds, right? They were G and H. G and H. So, let's look for a moment at these two, G and H. What would be the greatest lower bound? What do you think between G and H? Well, following the definition of greatest lower bound, we can see that the greatest of these two is G, because if we have some other lower bound like H, H is smaller than G. So this would be then the greatest lowest bound. And in case of the least upper bound, remember that the upper bounds were only A. Well, the least of the upper bounds are going to be A because it's the only one that we have. So even if there are maybe many lower bounds and many upper bounds, when we talk about the greatest or the least, then it's going to be only one. So we have a theorem that says that if a greatest lower bound of x and y exists, then it is unique. And the same is true for the least upper bound. So in case that exists, it will be unique. Let's take a look at this more complicated diagram here. So let's pick, for instance, 4 and 7. What would be lower bounds for 4 and 7? Well, let's start checking. Is 8 a lower bound for 4 and 7? No, because 8 it is less than 4, but 8 is no less than 7, right? So I don't have a way to go to 7, let's say, with this line. So 8 is not going to be. What about 10? Well, 10 is less than 7, but I don't have way to go to 4. So 10 is not going to be either. Let's see 9. 9 is less than 7, but is no, I don't have way to go here to 4. So 9 is not going to be either lower bound for 4 and 7. What about 11? So 11 can be, right, because 11 is less than 4 and 11 is less than 7. Okay, so 11 is one lower bound. Let's see about 12. Is 12 a lower bound? Well, 12 is less than 7, but I don't have way to go to 4 from 12. So in this case, the only lowest bound that we have is 11. So this is going to be also the greatest lower bound. Let's see about upper bounds. So we have that 2 is not an upper bound because 4 is less than 2, but 7 is not less than 2. What about 3? 7 is less than 3, but 4 is not less than 3. Is not. What about 1? Well, 7 is less than 1, that's good, but 4 is not less than 1, so 1 is not going to be. So, in other words, there are no upper bounds in this case. Okay, so we have 4 and 7, two elements that they don't have an upper bound. So that's why it's important in the definition, in this theorem where we said that the greatest lower bound is unique, it's important that we said if it exists, right? Because in that poset, for instance, it doesn't exist, so it's not unique because it just doesn't exist. Okay, the posets in which the greatest lower bound and least upper bound actually exist are very important kind of posets and have a particular name. These are going to be called lattices. So we are going to say that a poset is a lattice in case that every pair of elements has a greatest lower bound and a least upper bound. So, in this example, for instance, you can check that this is true. You take not just these two that we already checked, but any other pair. For instance, these two. Let's take these two and let's find out what is the greatest lower bound and the least upper bound. So, for instance, let's see the lower bounds. So the lower bounds for this one, so let's see, is E a lower bound? Well, it's smaller than B, but it's not smaller than F, so it's not. What about F? Is it a lower bound? Well, F is smaller than B, and is smaller than itself. Remember the loops that we have. So F is a lower bound. So who else is a lower bound here? Well, B is not, because B is smaller than itself, but B is not smaller than F. So we had that F is a lower bound. E was not. Let's say H. Is H a lowest bound? So we have that this is less than B and this is less than, so H is also. So this is the set of our lowest our lower bounds. So F and H are lower bounds for F and B. Now, which one is the greatest lower bound? Well, the greatest one is going to be F, right? So this is the biggest of the F and H. So that's going to be the greatest lower bound. In the same way, you can find the upper bounds, etc. But in this one, I'd like you to try with every possible pair, and you will see then that for every pair, there is a greatest lower bound and least upper bound. And in the case that happened, in the case that we actually are in a lattice, this greatest lower bound and least upper bound have a particular name. So the greatest lower bound is going to be called the mid of x and y, and is going to be noted this way. And when we consider the least of the upper bounds, it's going to be called the join, and the notation is going to be this one. Try to look now back at all the posets that I was mentioning before. Try to check which ones are lattices, and also check how much is the mid and the join in each case.